Okay, so this is going to be a brief demo on brief lesson on area and volume, right? Just area plus volume. And then right after that, we're going to jump into our free response question. So first question you have to ask is, how do you find the area of a curve? Well, for instance, if someone was given to find the area of y equals x cubed from 0 to 3, we know that. So the way you would solve this area would be from 0 to 3 x cubed d of x, right? And let's say if someone, the test answer wanted the area from -3 to 0, right? -3 to 0. You would evaluate it like this. So just, we're going to actually go over this in our free response, basically, but this would be a positive area, and this would be a negative area right off the bat, because this is above the x-axis, this shaded region, so it's positive. This is below the x-axis, this shaded region, so it's negative. And then if the test wanted from -3 to +3 of x cubed, that would actually be 0, because you're that's adding the negative to the positive, and they cancel out equally to 0. So that's how you basically do area. And then I'm sure you guys probably are, you would add the dx's, my bad. So I'm sure you guys know how to evaluate these integrals already, but just because, I'll just go through it real quick. So that would just be 1/4 x to the 4th 30. That would be how you would evaluate. You plug in your 3 there. 3 to the 4th power is 81 for a final of 81 over 4 units cubed. So this would just be positive 81 over 4. That would be negative 81 over 4. That would be 0. Hopefully that would make sense. How I arrived at those answers. So that's basically area. That's it. We're going to go more depth in this in the free responses, but this is just to fulfill the lesson requirement, because we have to do a lesson on this stuff first. Next step is volume. And what is volume? Volume is an extension of, volume is an extension of area. These, with area, you took the integral of these slices, infinitesimally small slices of this, and as it approached infinity, each slice got so small that this integral had basically an exact representation of the area. So similarly, volume is also slices too. Everything is slices basically in calculus for area volume, except these are actual these slices we call them cross sections. That's how volume is calculated. It's through cross-sectional slices, whereas these are kind of like linear, like thin slices. So for cross-sectional slices, for instance, this is actually a free response problem right off the bat, so I'm not going to go too deep into this, because otherwise I'd be just saying the same thing. But to evaluate something like this, for volume, you would basically taking circular cross sections here, and the formula to get a circular cross section would be area is pi r squared, right? So then the volume of this would just be the pi times the integral of f of x squared. And this is going to be more elaborated in the free response, because this is basically the radius, this distance, which is also f of x. Quite frankly, if they asked you, so this is equals circle, with if they wanted semicircle, right? So they might ask you a semicircle with radius x. Well, that would just be volume is pi half would be 1/2 pi, because a semicircle would only be half, because it's a semicircle. It's not a full circle. Semicircle is kind of like half of that, so it's only going to be half of the volume. So that's the equation for a semicircle. And then if they had a isosceles triangle, isosceles with legs perpendicular, with legs as the base, basically to solve that would just be well, actually, let's do square first. If we had square sections, if you consider a square, that would kind of look like that. All these infinite square cross sections, I really can't draw that well, but all these infinite square cross sections perpendicular. What is the area of a square? Area squared is a side square, so that would be volume would just be the integral of f of x squared. So square is actually the simplest to do. And then triangle, isosceles triangle of base with the leg perpendicular, not the hypotenuse. The leg would actually, not the hypotenuse, the leg, right? Just remember that. So that would be f of x squared 1/2, because you know the area of a square, area of a triangle is, if you took a square like this sheet of paper and you fold it in half, that would be a triangle. So the area of the cross section would be half of that of this. So it's basically this one divided by 2 is that. So that's the that would be a isosceles triangle of legs. And then if we had an equilateral triangle, there's only 3 cases really. There's equilateral isosceles. This for equilateral triangle with sides of x. So an equilateral is slightly different, right? An equilateral is 60, 60, 60, whereas isosceles with the legs would be 90, 45, and 45. So if it was an equilateral, the formula is the integral of radical 3 over 4 of f of x squared. And the way we arrived at radical 3 over 4 is because if we draw our isosceles triangle, you could think of this as x, right? So if we had our function, remember our parent function, radical x, it would kind of look like this, where each cross-section is these isosceles triangles, if that makes sense. And it's kind of hard to draw, but basically the radius we have is x, right? So x, so then each section would be 1/2 x here and 1/2 x there. And because this is a 30 degrees and this is 90 and that's 60, you could use trigonometric ratios to find all of them. So if you use your trigonometric ratios, the area is 1/2 base times height, right? So base, right? What is the base? The base is what? It comes out to be what? Like square root of 3. And what is our other thing, right? Square root of 3 over 2 is this height. So when we multiply all that together, 1/2 times square root of 3 over 2, we get our square root of 3 over 4 x squared. So that's how, those are the only 3 cases. So that's how you solve. So that's how you do the equilateral triangle. That's the equation. So if you forget, if you forget these memorizations, you could just draw it out like I did, and then you would arrive at the same conclusion, basically. Okay, so I'm just showing area and volume real quick. So the first says, let R be the region bounded by the x-axis, the graph of y equals radical x, and the line x equals 4. Okay, so right off the bat, y equals radical x, boom. X equals 4. That's that line. And bounded by the x-axis, so that's what we're solving for. To find the area of this region, we could call it R. Okay, so the area of R, so this is part A, find the area of R. So A. So R is actually going to be the integral from 0 to 4. Those are boundaries. Radical x. So radical x is basically x to the half power. And first off, to find the area of a function, you simply integrate it with respect to the endpoints. So basically we have x to 1/2, right? So to integrate that, for x to 1/2 is like a polynomial, so we add 1 to the exponent. So 1/2 plus 1 is 3/2. But we also multiply the coefficient by the reciprocal of our exponent. So the reciprocal of 3/2 is 2/3. So that is our equation. Basically now we have to evaluate that. So the way we evaluate that is we have, right, so we plug in our 4, because 0 to whatever is 0 to the 3/2 is just 0, so we just don't worry about that. So the 4 is 4 cubed. 4 cubed is 4 times 4 is 16, times 4 is 64. 64 to the half power is 8, and 2/3 times 8 is 16/3. And we have a units squared since it's area. So then part B. Part B says basically they want to know find the value of h such that the vertical line x equals h divide this region R into two regions, regions of equal area. So we have this line h. We want to find basically this section to the left of h has to be equal in area to the section to the right. So if we know the total area is 16/3, then each section has to be half of that because they're equal. So 8/3 and 8/3 are on each section. So now the question is just what is that h? So we're going to do this by setting up an equation. So we have, so this left section is the area from 0 to h, radical x dx. And we're going to set that to equal to 8/3. Question is, what is that h? Well, quite frankly, the best way to solve that is just to kind of repeat what we did above. So the integral of x is simply 2/3, right? But instead of x, we're using h, right? So 2/3, h to the 3/2 equals 8/3. You multiply each side by the reciprocal of this 2/3 to clear out the fraction. So then we have h to the 3/2 equals 4. We simply square both sides to get rid of that fractional 1/2 exponent. H cubed is 16. Cube root both sides. That is our answer for part B. Hopefully that makes sense. And then we have to do part C, so I'm just going to clear that out real quick. That's okay with you guys. So real quick, part C and part D. So just to recap what we did before, we had our function, right, of y equals square root of x. Part C, find the volume of the solid generated by R when it is revolved around the x-axis. So this is the x-axis, right? And find the volume when this function is revolved around it. So if we revolve it, we're revolving like 360 degrees, right? So then we have this three-dimensional shape. Hopefully we could draw that slightly better. There we go. So we have this three-dimensional shape, and this is basically, you would call that a paraboloid, basically. That's the fancy name of it. And, well, we want to find the volume of that. So, first off, the way we're going to solve that is, when we take the volume of something, we're basically taking slices, and we're adding up all the slices. And the slices are like infinitely thin. So if you could imagine, each slice of this would be a circle. And what is the area of a circle, right? The area of a circle is pi r squared, right? So in the same way, we're going to find our volume by integrating 0 to 4, right? Well, what is our radius, right? Our radius is simply this distance, right? Well, what is that distance, right? Because this is the whole diameter, so that is the radius. So what is this distance? This distance is square root of x. All right, because in this function, the radius is changing. Like you could think of a cylinder. The cylinder has a constant radius, right? But this is a paraboloid, so it changes at each point. So we're taking the integral of this to account for this changing radius. So that radius is simply radical x. So area is pi r squared, so pi r times square root of x squared. So we're finding the integral of that. So what is that? What is square root of x squared? That's simply x, right? So what's the integral of x? Integral of x is 1/2 x squared, right? From 4 to 0, pi. That's our function. So 4 squared is what? 16. 16 divided by 2 is what? 8. 8 pi. So that's that. So then part D is almost a repeat of what we did before. It says the vertical line x equals k divides the region R into two regions such that the volume, when these two regions are revolved, they generate solids of equal volume. So remember before we had equal area. This is just a rehash of that, except it's equal volume. So you can imagine a line x equals k. We're going to call that k, right? And it's basically cutting this paraboloid. That's in half. That's the technical term for it. So we got to find the what that line is. But before it was h, so now it's k. So before we took the area and we divided by 2. Right, so then we're just going to take the volume, this volume, and divide it by 2. So basically volume, right, is pi times the integral of, instead of 4, it's going to be k, because we're basically doing problem B again, except we're using volume. And half of 8 pi is 4 pi. So remember in part B we were solving for h, now we're solving for k, and we're setting this up equal to half of this volume. So first step, you could just simply divide the pi's out, right? So then what we have left is, well, what is the integral of x to the radical x squared, right? So that's simply 1/2 x squared like before, except instead of x it's k, because the 0 just doesn't matter, because 0 squared is simply 0. And then we multiply both sides by 2 to clear out this fraction, and then square root both sides, and we get k is square root of 8. So then that is part D. So that's basically, we finished off that free response. So we have this last free response, which is 2012 question 2. So the way we're going to approach this is, well, it says let R be the region in the first quadrant. Okay, first quadrant bounded by the x-axis, and the graphs y equals ln of x. So ln of x is the inverse of e to x, so this is our ln of x. And this is our 5 minus x. Right. So it wants to find this area of R. So we could say A. So R is basically going to be a composite function, and what that means is it's two functions added together. So that basically, the way you do that is we have the integral from 1 to, we didn't name that yet. Well, actually, I'm getting ahead of myself. The first step is finding this intersection point, because that is going to be our, I guess, domain points of the integral. So this intersection, we have to find the x value. So if we number this, it looks to be like 3.5-ish or whatever, but we want an exact value. So to solve that, we simply set these equations equal to each other, and you put that in your graphing calculator. And if you do that, you get 3.693 as your x value where they intersect. So basically, the intersection is 3.6934. So we were close at estimating at 3.5. So when we set up our integral, we're integrating from 1 to 3.6934, right? But what is this function? ln of x, right? Plus integral 3.6934 to 5, because it ends at 5, of 5 minus x. Right, so how are we supposed to do that? And we would want to add dx at both ends, so we don't get in trouble for that. So how are we supposed to do that? Well, we have ln of x, right? So what is the integral of ln of x? That is 1 over x, right? What is the integral of 5 minus x? Well, the integral of 5 is 5x, integral of negative x is negative 1/2 x squared. And then to evaluate that, it's simply, we'd have 1 over 3.6934 minus 1 over 1. Because, and then we'd add that to basically 5 times 3 point minus that function squared. Actually, did I write 1 down here? That's supposed to be a 5. Actually, I messed this up. This is supposed to be a 5, and that's supposed to be 3.6934. So we basically do that, and then you're going to subtract that from, we're going to subtract that from 5. Well, actually, getting ahead of myself. This messed up. Okay, so this is a second free response, so we're going to do this real quick. So find the area of R. R is this, and it's bounded by the graphs of x-axis, graphs of y equals ln of x, and the graph 5 minus x. These two functions meet at some intersection point, so we're finding the area of that. So we need to find that point first. So that point, you would basically set up an equation, and you'd put that in your graphing calculator, and you would get x equals 3.6934. This you'd have to put in your calculator. You really can't solve that by hand. You need a calculator for that. So, A, find the area of this region. So the area is going to be so that's our area function. So it's 1 to 3.6934, 1 to 3.6934. That accounts for this. And then we have 3.6934 to 5, 3.6934 to 5. So that's our function. So the integral of, what is the integral of ln of x? That's 1 over x. What is the integral of 5 minus x? That's 5x minus 1/2 x squared. And it's the sum of these two functions, right? That's our area. So you would put that in your calculator, and you would just do, right off the bat, to evaluate this function would just be 5 times 5 minus 1/2 of 5 squared. And we're subtracting it from this guy, which is 5 times 3.6934 times 5 times 1/2 of 5. Well, actually, of 3.6934 squared. And that counts for this part. So then we have to do this part, and this part would be 1 divided by 3.6934 minus 1 over 1. So it's the sum of this part and that part, and when you evaluate that, you're basically going to type that into your calculator. There's no way you're going to do that by hand, and you get 2.986. So if you were to type that mess into your calculator. So then, yeah, part B says the region R is a base of a solid. Okay. For the solid, each cross-section perpendicular to the x-axis is a square. Okay. Right, but do not evaluate an expression involving one or more integrals that give the volume of the solid. So basically, you could think of squares popping out of this thing. So if we were to visualize that, you would just basically see a bunch of squares that were perpendicular to the x-axis, so we have them perpendicular. So if you'd have all these squares kind of like a loaf of bread all like together, and you'd have to find that. So how are we supposed to do that? Well, basically, remember before we were doing this ring thing, instead of rings we're using squares, these square slices. So what is the area of a square? Area of a square is area equals side squared, right? Or length or whatever. Well, what is this s? S is simply the value of ln of x, or 5 minus x. Right, so simply volume is the integral of 1 to 3.6934. And it tells us to write but do not solve, so that makes our lives a little bit easier. So remember, it's side squared, right? So it's ln of x squared, because the area is a side squared. And then we're adding that to the 5 minus x. And don't forget the dx. So that is equation for a volume of this basically thing where it's basically a loaf of bread with all of these square cross sections. Because this integral, we're basically, each cross section, which is a square, has a very infinitesimally small thickness. And that is what that integral is accounting for. So, yeah. Part C says, alright, let's, what does part C say? Part C says the horizontal line y equals k. So y equals k would actually look like this, right? Y equals k. So if you want me to draw that, yeah, so you could forget about this vertical line for now, I guess. So the horizontal line y equals k divides R into two regions of equal area. Okay. So if we were to redraw that, because this is getting a little bit messy, if we were to redraw that, we have y equals k. That's our ln of x, and that's our 5 minus x. And it divides this region R into two equal sections, right? What is the equation, right? Write but do not solve an equation whose solution gives the value of k. So the thing about this is a horizontal line. So to find an integral, you'd have to basically rotate this 90 degrees, if that makes sense, because then your equation, because we have to have it with respect to y, if that makes sense, because we want to find the area of this section and the area of this section, and we're going to set these, basically we're going to set that to half of something, right? So the way we're going to get this rotated 90 degrees is simply using the inverse. Well, actually, not the, well, actually, yeah, so the inverse. So basically what we have here is the area of this function would be y. So we have these two functions, right? And we need to find the inverse, right? Because they're getting rotated. We're having it, instead of respect to x, like we're differentiating, we're integrating with respect to x in this example. But in this example, we're integrating with respect to y. So we have to flip-flop x and y, if that makes sense. So ln of x, y equals ln of x. So this actually becomes x equals 5 minus y. And this, we're switching these two. And we evaluate that. That becomes e to the y. If we circle of life this. So what are we solving here? Well, it solves it into two equal areas, right? So remember, if this area, remember before in the paraboloid problem, we took our volume and we divided it in half. Similarly, we're setting this volume to 1/2 of this 2.986, right? So paraboloid, so we're setting it half because it says two equal areas. So then, furthermore, we have this function from 0 to k, because it's finding this y equals k line. And we're basically going to have 5 minus y minus e to the y equals that, because when we rotated this 90 degrees, our 5 minus y was on top minus e to the y, so it's this top area minus, so it's this top area, right, minus this bottom area, which is this section, and then this section, when you subtract, it gets eliminated, and we're just left with this clean kind of like blade looking thing. So that's basically what we're doing here. So it's the top, when it's rotated, right, 5 minus y minus e to the y equals 1/2 of our area, 1/2 of that. And it says that we don't have to solve it, which is very nice of them. So that's about it for today. Hopefully you found this, I guess, useful or whatever. So thank you for your time.